Good afternoon, class. In today's video, what I'd like to do is to go over momentum and basically the concepts that go behind it, but also to go over a little bit of the nuts and bolts of the equations that are used in these various equations. So, for example, momentum is given by the letter P, and I'm sorry, unfortunately, I don't know why it's P, even though because power is P, and there's no P in momentum at all. So, but that's the name that scientists have given it since time immemorial, so there we go. We're kind of stuck with it, unfortunately. Momentum is mass times velocity. So if you were to translate that equation, it would be saying how momentum is how mass moves. So any kind of movement that mass has a momentum associated with this. This statement is in general true. There is one notable exception, which is light, and we will get to that when we talk about special relativity and general relativity later on in this course. The one I did want to focus on, especially for the purposes of this video, is this force equation, which we remember as F equals ma, or mass times acceleration, but we can also write acceleration as velocity over time, which would be mass times velocity, which is momentum, over time. So you could rewrite the force equation as delta P over delta T. Now some of you are going to ask me, but Mr. Achiu, what does delta mean? And so that's why I wrote this over here, just to show you that these two are equivalent. So delta means change in, so the change in something. So I could say for the change in momentum, it'll be the final momentum minus the initial momentum. That's why there's a subscript F and a subscript I. Same thing with time. If I've got a change in time, or delta t, it's going to be the final time minus the initial time. Now, normally in your measurements, especially during all of your labs, you generally didn't measure delta t, or at least so you thought, because instinctively your initial thought was initial time was 0, and because that's where all of our clocks start. We always start at 0. This is not always true. It depends on the situation and the scenario that is being given, but it's a fair assumption to say that t initial will generally be 0. So most people don't really think about it. In fact, even with the initial momentum, a lot of times people will generally say, "Oh, that's 0. We'll start at 0. We'll just count the final momentum." So you would be excused if this triangle, or which is actually the Greek letter delta, seems a little bit strange, because you would generally think that this part has no meaning in your everyday dealings with these equations. Now, I did want to so given that, I wanted to go over now this equation, force equals delta P over delta T. I want to write it bigger so that we could kind of see some of the ways that this goes. So I had a couple of statements here. So force and change in momentum are what we call directly proportional. What does that mean? So if I were to translate that, I would say that if this force goes up, this delta P, this change in momentum, must go up, assuming everything else in the equation is constant. So whenever we talk about proportionality, we always have to assume that whatever I'm comparing it to make things proportional, I have to assume that everything else in the equation is constant. So in this case, we would say if you had your delta T, or your change in time, is constant, then if the force goes up, it must be because there's a change. The change in momentum is going up as well. This would be in the case of something like, let's say I dropped a ball, and the contact time was exactly the same every single time. Then in that case, if the force was measured as something different, then it would be because I was maybe throwing the ball harder, or I was throwing the ball up, and so it hit the ground at a different rate, or a different force. So then, and the reason for that is because I would have had a change in momentum. I would have been changing the velocity of that ball when it was falling to the ground. So that would be force and change in momentum are directly proportional. Now, what does, so that's wonderful. What does it mean though, what's the relationship between force and change in time, or delta t? So they are inversely proportional. And what that means is that as one goes up, the other must go down. And again, we have to consider this from the viewpoint of keeping everything balanced. We're keeping everything constant, everything else constant in this equation. So in this case, it would be delta p. So assuming that delta p is constant, if this delta t goes up, the force must go down. You can actually see this. Usually, I can give an example from football, American football, especially for people who are from around internationally. I should be specific, American football. When we have, especially because some people would get mad if I start talking about catching the football. People would be like, no, you can't do that. Sorry, wrong sport. American football. Let me just make my plug there. So in American football, when the receiver catches the ball, and notice they have their hands out and they bring their hands in, what they're doing, and of course you would call that soft hands, that would be increasing this change in time, because you can't change the momentum. The momentum of the football as it's being thrown by the quarterback is determined by the quarterback. The receiver can't do anything about that momentum. It will always be whatever the momentum the quarterback gave, and so the receiver has to increase the contact time because everybody's hands have a certain amount of force that they can withstand before the ball slips out, or just bounces right off of your hands, and then you've got a dropped pass or a deflection or something like that. So this force needs to be as low as possible, which means that the contact time must be as high as possible. And that's why you see the football players will receive the ball this way. Either they'll catch it towards their chest, or they will catch it and bring it to them. That's why football players will tend to do that. If for those of you who are boxing fans, that's also why. And so if I was to stand here and somebody were to throw a punch at me, that's the reason why you always see them rocking back, and it seems like they're taking these superhuman punches. These wild punches are coming at them. They can somehow get hit by them and not get knocked out, and it's amazing to see. But really what they're doing is they're increasing that contact time. And you can actually have a little bit of a demonstration of this, and if you want to try this now, you can. You can either stop the punch. If you punch your hand, you can stop the punch just by keeping it stiff. You can move move towards the fist, so it would sound like this, and that's a little bit louder. Or I could move with the fist, and as you notice from the sound, it was probably very soft. If I were to do it even better, it wouldn't make any sound at all. That's because I'm increasing the contact time, so the force is going significantly down. That's what it means to be inversely proportional. By the way, I thought I'd just make a mention here, and if you want to ask me this during class, you can. This also means if you increase this change in time enough, what that means is that you can actually catch anything. So if you wanted to catch a bullet, for example, and you had the right setup, and you could bring the bullet in as long as it takes for the force to come down, so it doesn't pierce your skin. There's nothing that in physics that says you can't do that. You can actually catch bullets if you want to. It just requires the kind of setup that is not possible for our limited human bodies, but it is possible if you really work at it. So things are to think about. In fact, that's why I like to call this equation the Superman equation, because if you want to do things that are really crazy, you actually can, as long as this contact time is high enough. You could do things like survive a fall. Like if you were to fall, even for me, if I was running and I tripped on the sidewalk and I kicked the sidewalk because some tree root has kept broke up the sidewalk a little bit. I kicked the sidewalk, I tripped over it, and I fell down. If I fell flat on my face, I'd probably get really hurt. But if I were to roll through it, then I wouldn't get hurt. In fact, I mean, maybe a couple scratches, but it wouldn't be some, like I wouldn't have a concussion or anything like that. So it's something to think about. Also, and the last part I put on here about delta P and delta T are being directly proportional. The reason I put that there was because in this case, what I want to do is I want to show you that if the force is constant, and this kind of helps because now everything is one side of the equation, we're holding one side of the equation constant, and we're not just holding parts of this part of the equation constant. So let's assume in this case that force is constant. If delta P goes up, then delta T has to go up as well. So for example, if this was 1 and 2, so the force was 1/2, then if delta P goes to 2, delta T needs to be 4, because this force cannot change, without other energy inputs or any other forces. If we're just talking about just like, say, like in my football example, the football being thrown, you can't if you can't change the force, what you have to, if you assume the force is constant, if this doubles, this has to double as well. That's what it means to be directly proportional. So that concludes my introduction on momentum and going over some of my one of my favorite equations in physics, mostly because this one makes me feel like a superhero. So I thought I'd end the video on that. Thank you guys very much. Good luck on your studies, and may the force be with you.